So in this section, 5.2, we're going to talk about polynomial division and the division algorithm. The division algorithm, the remainder theorem, polynomial long division, synthetic division, and we're going to learn how to construct polynomials with given zeros. The reason we care about polynomial division is because it allows us to guess at factors to our polynomials and then divide them out. And if they come out evenly, we know they're a factor. And that's sort of what the division algorithm tells us. So if we have two polynomials, P and D, and the degree of D is going to be smaller than the degree of P. Such that we can divide P by D. Then once we do that division, there's going to be unique polynomials Q, kind of think quotient here, and R, think remainder, such that our larger degree polynomial P is equal to the quotient times D plus the remainder. Either the degree of the remainder R is less than the degree of the divisor D, or the remainder is going to be 0, in which case we're going to say that our polynomial D divides evenly into the polynomial P. If the remainder is 0, then the remaining two polynomials Q and D are going to be factors of P. So you see how if we can divide our polynomial by another polynomial and get no remainder, then we will know that that other polynomial is a factor. So the number K is a 0 of a polynomial if and only if the linear polynomial x minus k is a factor of P. Okay. That's kind of what we already know from when we have solved the equation P of x equals 0. Okay. The remainder theorem tells us that if P, our polynomial P, is divided by the other polynomial x minus k, then the remainder is actually our polynomial P evaluated at k. So the remainder theorem is a kind of a neat way to evaluate polynomials as well. All right, in this first example, let's do some polynomial long division. If we want to divide the polynomial x squared plus 2x minus 24 by the linear polynomial x plus 6, we'll set it up actually just like we used to set up our old type of long division. Okay, make sure that the polynomial, the larger polynomial is written in descending order of degree. Okay, and we only are going to look at this first term of our divisor when we are trying to see how many times this goes into our main polynomial. Okay. So we're going to do this first term and the x squared. So how many times does x go into x squared? Well, it goes in x times. And I like to write these answers directly above the same degree terms. You don't have to do that, but that helps me. So x goes into x squared x times, and then we, just like regular long division, x times x plus 6 is going to give us x squared plus 6x. Now, all of that stuff, as you remember from long division, needs to be subtracted from the original polynomial. And we end up with a negative 4x minus 24. Then we ask ourselves, how many times does x go into negative 4x? Well, it goes in negative 4 times. Then we do the negative 4 times the x plus 6, and we get negative 4x minus 24, and we subtract that to get that a remainder is 0. Because the remainder is 0, we know that x plus 6 is a factor of the polynomial x squared plus 2x minus 24. All right. And the quotient is x minus 4, meaning that x minus 4 times x plus 6 gives us x squared plus 2x minus 24. So we can actually now rewrite our polynomial as x plus 6 times x minus 4. So here's just an overview of how to perform polynomial long division. If you want to pause this and read through or even take a screenshot of it, you can do that. All right, let's do another polynomial long division. This time we've got a 5th degree polynomial, and we are dividing it by a 2nd degree polynomial. All right. I put this 0x placeholder in there because I just like to see every degree of the polynomial, even if one of those terms is 0. We do the same thing. We're just going to look at the 2x squared. How many times does 2x squared go into 6x to the 5th? Well, it goes in 3x to the 3rd times. And if it helps you think backwards, you kind of say, what do I need to multiply 2x squared by to get 6x to the 5th? That's going to be 3x to the 3rd, right? And again, I just like to write it above the same degree term. We're going to multiply that 3x to the 3rd by everything in this polynomial and subtract it from our original polynomial, and then repeat the process. How many times does 2x squared go into negative 2x to the 4th? Well, that's going to be negative x squared times. And we're going to multiply that by the whole polynomial, subtract it all, and then do it one more time. How many times does 2x squared go into negative 12x squared? Negative 6 times. We're going to multiply that by our original polynomial, do the subtraction, and we see that we get negative 6x minus 1 left over. We can't divide negative 6x minus 1 by 2x squared because negative 6x minus 1 is a lesser degree than 2x squared. So at this point, we're going to call that our remainder. So negative 6x minus 1 remains to be divided by our original polynomial. So let's go back for a second. We can divide it by the 2x squared minus x plus 3, and we get the 3x to the 3rd minus x squared minus 6. But this piece, this negative 6x minus 1, remains to be divided. So what that looks like is we have that 3x to the 3rd minus x squared minus 6 plus the stuff that remains to be divided by our polynomial. Be very careful about that negative sign when we are subtracting, okay? A good way to not forget that negative sign and to distribute it is to put parentheses around the polynomial being subtracted. What I'm talking about is this right here. So we multiplied our 3x to the 3rd times our 2x squared minus x plus 3, and we got this 6x to the 5th term or polynomial. We subtract that whole thing. So that's why we put the parentheses to say we're subtracting the whole thing, because we are subtracting 6x to the 5th. We are subtracting negative 3x to the 4th, right? That's why we got a positive 3x to the 4th to add to our negative x to the 4th. So this negative sign has to get distributed into all of these terms because we're subtracting this whole thing. So that's what you want to be very careful of in this polynomial long division. There's another way to do this in the event that the divisor is x minus k. So if our divisor is a linear divisor, there's actually a shorter way to do this long division, and it's called synthetic division. Basically, what we do is we write down the k, and we follow that by all the coefficients of the dividend in our first row. And then we are going to take the leading coefficient of the dividend and put it in our row 3. And then we multiply our k. And remember, k is essentially the 0 if we have a factor of x minus k. We're going to multiply our k by that value placed in the bottom row, the leading coefficient essentially, and put the product in the next column. Then we add these values to give us a new value in the bottom row, and we repeat this process. Right. The numbers in the bottom row end up being the coefficients of our quotient plus the remainder. All right, so here's how we start. We have this polynomial negative 2x to the 4th plus 11x to the 3rd minus 5x squared minus 3x plus 15. And we essentially are dividing this polynomial by x minus 5, or we're dividing this polynomial by the linear factor if 5 is one of our zeros. So we put the 5 in that little box and we list all our coefficients in the first row. Make sure that if you have any missing terms here where the coefficient essentially is 0, that you put that 0 there. All right, and then we do the first step. We just drop that leading coefficient to the very bottom line. And then we say, what is 5 times negative 2? It's going to be 10. And so we'll put the, negative 10, we'll put the negative 10 there. Okay. Then we add those 2 rows and we get a 1. What is 5? What's 5 times 1? It's going to be 5. We add these 2 rows and we get a 0. What's 5 times 0? It's going to be 0. We add the 2 rows and we get a negative 3. What's 5 times negative 3? It's negative 15. We add those 2 rows, we get a 0. By getting a 0 here, that tells us that we have no remainder and that x minus 5 is a factor of our p of x. Okay. Knowing that that's a factor of our p of x, we can factor p of x as x minus 5 times this polynomial here is the polynomial we got from the coefficients that were remaining. Okay. So this is a 4th power, or sorry, since our polynomial was a 4th power and we divided out a single power of x, the negative 2 is the coefficient on the 3rd power of x. The 1 is the coefficient on the 2nd power of x. The 0 is the coefficient on the power of x. Notice we have no x term here. And the negative 3 is our constant term and no remainder. So we were able to use this synthetic division just like we would use polynomial long division. It just is a little bit faster and less stuff to keep track of, but it only works if we are dividing by a linear polynomial. Okay, and keep in mind the linear polynomial we're dividing by is x minus 5. In that case, 5 is a solution to this equation set equal to 0. So 5 is the number we put in the corner, or whatever the 0 would be if x minus this number is a factor. Let's do synthetic division one more time with another polynomial has some terms that have coefficients of 0. So in this polynomial p of x, we have 3x to the 8 plus 9x to the 7 minus x to the 3rd. Notice we don't have any x to the 6, 5, or 4 terms. So their coefficients are essentially 0. So when we write them out in synthetic division, this is x to the 6, 5, and 4 terms. They have coefficients of 0. We have to have those zeros there. Now we're going to divide this polynomial by x plus 3. 0 is a negative 3. So we set up all the coefficients of these terms here. We drop that first term into the bottom row, and then we just say negative 3 times 3 is negative 9. Add them together, we get 0. Negative 3 times 0 is 0. Add them together. We keep going, keep going. Negative 3 times negative 1 is 3. Add them together. we get 0. -3 times 1 is -3, and we end up with a -4 in the remainder spot. All right. So now this 3 is going to be the leading coefficient for our x to the 7 term, 6 term, 5 term, 4 term, 3 term, x to the 2, x to the 1. This is our constant term, and this is our remainder. Okay. So that also tells us that this polynomial P is not divisible by x plus 3, meaning that x equal to -3 is not a solution. Excuse me. Now, let's do an example of synthetic division with complex numbers. So in this fraction, you see the polynomial P of x is the polynomial in the top, and we want to divide it by x minus 1, or x minus I, sorry, x minus 1 minus I. So here's the polynomial division that we're doing. And here our polynomial is x minus 1 plus I. So the value of x that would make this 0 is going to be 1 minus I, okay? So 1 minus I is the 0, essentially, or the root. 1 minus I is the root that we are checking to see is in this polynomial up here. Now, we do have these parentheses. These things in parentheses are just the coefficients of our x squared term and our x term and our constant term. So we're going to work them the same way. These are just each of the coefficients of the polynomial we're dividing by, and this is the root of this other polynomial. So we go through the same process as we did before. We get a remainder of 0, and that tells us that 1 minus I is a root of our polynomial. Okay. As we go through this, though, you want to be very careful that you are using your complex number arithmetic. Anytime you get an I squared, that simplifies to a -1, right? Because I is the square root of -1. So I squared is just a -1. And we have our quotient. Sorry, and that's complex number synthetic division. Take a second, maybe let's take a second and go through this division so that you understand how complex number multiplication works. All right, so we multiply the -3 times 1 and the -3 times -I, and that gave us -3 plus 3i. Then we just do the addition here. We got 2 plus I, okay? Then we multiply 1 minus I times 2 plus I. When we do this, the 1 times 2 is 2, but the -I times I is going to be -I squared, which becomes a +1. So that's what gives us the total of 3. Okay. And then the 2 times -I and the 1 times +I is what gives us the -I. Okay. So when your i's are getting multiplied by each other, I squared becomes a -1. And if there's a negative on the outside, that gets applied afterwards, making it a +1. Okay. We end up with a -1. So we do -1 times 1 minus I. And then we do the subtraction, we get 0. So just kind of a recap here. When we did that 1 minus I times 2 plus I, when we did this multiplication here, 1 times 2 is 2. 1 times, what do we have? 1 times I is I. And what do we have? Our I, here we are. The -I times I becomes negative I squared. Okay. So sorry, this first negative I came from 2 times negative I plus 1 times positive I gives us just a net negative I. But the negative I times I is negative I squared. I squared becomes -1. So we have negative -1, which is a positive 1. That positive 1 plus 2 is 3. All right, so we can use all this actually to create polynomials with whatever zeros and end behavior we want. Okay. So if we want to construct a polynomial that is 3rd degree and it has zeros of -3, 2, and 5, and it goes to, so y goes to -infinity as x goes to +infinity, we can do this. We want a 3rd degree polynomial and we have 3 zeros or 3 roots. So we're definitely going to have those 3 factors. Okay, we definitely have these 3 factors. That gives us our zeros. But we want our polynomial to go to -infinity as x goes to +infinity. And if we multiply all these guys out, we're going to have a positive leading coefficient, and we really need it to be negative. So we're just going to multiply by a -1 to kind of flip that end behavior. And we get this polynomial -x to the 3rd plus 4x squared plus 11x minus 30. And you can see that the end behavior is going to be how we want it, and we're going to have the zeros where we want them. That polynomial looks like this. As x goes to -infinity, y goes to +infinity. As x goes to +infinity, y goes to -infinity, and we have those 3 zeros. Let's construct one more. Let's make a 4th degree polynomial with these 4 zeros and a y-intercept at 0, 15. So we've got our linear factors, which are easy to put in there. We've got 4 linear factors, so we've got our zeros, but we want the y-intercept to be at 0, 15. And if we plug in a 0 into this function, y actually is 30. So that's not the right y-intercept. If we want the y-intercept to be 15, well, then we need our function to essentially be cut in half to make it 15 instead of 30. So we'll just multiply our function by 1/2 and multiply it all out. And that function will have these 4 zeros and cross the axis at 0, 15.